Picture a man so dedicated to thinking that he blinded himself to avoid distraction. A philosopher who laughed at everything, including death itself. Someone who spent decades wandering the known world, then returned home to be prosecuted for wasting his inheritance. His name was Democritus, and he invented the idea that would eventually become modern science, that everything in the universe is made of tiny, invisible particles moving through empty space. He called them atoms, 23 centuries before anyone could prove they existed. We're going to follow this strange figure from his birth in a wealthy merchant family, through his transformation into the laughing philosopher, from his revolutionary ideas about reality to his bitter old age in a city that had forgotten him. This isn't a story about a man who changed the world in his lifetime. It's about someone who saw the truth so clearly that it took 2,000 years for everyone else to catch up. The city of Abdera sat on the northern coast of the Aegean Sea, in the region the Greeks called Thrace. By the standards of the classical world, it was a backwater. Athens had the Parthenon, the playwrights, the philosophers holding forth in every marketplace. Sparta had its legendary warriors. Abdera had grain merchants and a reputation for producing idiots. There was even a Greek expression, as stupid as an Abderite. Into this unlikely setting, around 460 BC, Democritus was born. His father's name is lost to history, though some sources call him Hegesistratus, or Athenocritus, or Damasippus. The confusion itself tells you something. Rich merchants didn't make it into the historical record unless their sons did something remarkable. And Democritus would do something so far beyond remarkable that we're still trying to fully understand it. The household was wealthy. Not aristocratic wealth, not the old families who traced their lineage back to heroes and gods, but merchant wealth. New money built on trade routes and cargo ships, on knowing which cities needed grain and which had surplus, on understanding winds and seasons and the movements of goods across the Mediterranean. It was the kind of wealth that made traditional aristocrats uncomfortable, wealth that came from calculation rather than inheritance. Young Democritus grew up surrounded by maps and manifests, by conversations about distant ports and foreign customs. The house saw visitors from across the known world, Egyptian traders who'd sailed from Alexandria, Phoenician merchants with purple-dyed fabrics, Persian officials travelling the King's Road. Each brought stories, and the boy absorbed them all. But here's what's strange. The ancient sources insist that Democritus was educated by Persian and Chaldean magi, not Greek tutors, not the usual rhetoric and poetry that wealthy Greek boys studied. His father, according to these accounts, had hosted King Xerxes during the Persian invasion of Greece decades earlier. As thanks, Xerxes left behind some of his wise men to educate the merchants' sons. Most historians dismiss this as legend. Xerxes invaded Greece in 480 BC, retreating in defeat. Why would he leave his magi as a gift? Why would a Greek family want Persian teachers after a war? Yet something in Democritus's thinking suggests exposure to ideas beyond the Greek world. His concept of the void, the idea that empty space can actually exist, was deeply un-Greek. Greek philosophers hated emptiness. Aristotle would later spend considerable effort proving that nature abhors a vacuum. But Persian and Indian thinkers had been comfortable with nothingness for centuries. Whatever the truth of his early education, one thing is certain. Democritus learned to think in ways that made other Greeks uncomfortable. His inheritance, when it came, was substantial. Some sources say it was 100 talents, an enormous sum. Others say less, but still enough to live comfortably for life. Most young men of his class would have invested in ships or land, married well, produced legitimate heirs, participated in civic life. Democritus did none of these things. He took the money and left. The ancient world was vast but knowable. You could walk from Greece to India if you had time and determination. You could sail to Egypt, to Phoenicia, to the Greek colonies scattered across the Mediterranean and Black Seas. And Democritus barely into his 20s, set out to see all of it. He went south first to Egypt. The Greeks had been fascinated by Egypt for centuries. It was ancient when Greece was young, its temples and pyramids already thousands of years old. More importantly, it had priests who claimed unbroken traditions of knowledge stretching back to the time of the gods. Mathematics, astronomy, medicine, the secrets of preserving the dead. The Egyptians knew things. In Memphis and Thebes, Democritus studied with these priests. He learned their geometry, developed not from philosophical abstraction, but from the practical need to resurvey fields after the Nile's annual flooding. He learned their astronomy, refined over millennia of watching the stars wheel overhead. And he learned something else, something the priests might not have intended to teach, that knowledge could accumulate over generations, that truth could be built piece by piece through careful observation rather than revealed in a single flash of insight. From Egypt, he travelled east. Persia, certainly. Babylon, where the Chaldeans had been mapping the heavens for 1,000 years. Some sources claim he reached India, though this is disputed. What's not disputed is that he spent years, possibly decades, away from Greece. While other philosophers sat in Athens debating the nature of being, Democritus was walking through deserts, sailing dangerous seas, learning from every tradition he encountered. He returned to Abdera changed. Not just older, not just more knowledgeable, but fundamentally transformed in how he understood the world. And almost immediately, he faced prosecution. The charge was squandering his patrimony. Under Abderite law, a man who wasted his inheritance could be denied burial in his homeland. It was a serious matter. To the Greek mind, proper burial was essential. The unburied dead wandered forever, denied entry to Hades, unable to find rest. The punishment wasn't just social disgrace, it was spiritual exile. Democritus defended himself by reading from his work, The Great World System. We don't have this text anymore. It's lost, like most of his writings, but the ancient accounts say it was impressive enough that the court not only acquitted him, but awarded him 100 talents and bronze statues in his honour. Think about what this means. He convinced a jury of merchants and farmers, practical men who measured wealth in land and goods, that his years of wandering and studying had been more valuable than any investment in ships or property. He made them understand that knowledge itself was worth more than money. Or maybe he just gave a really good speech. The sources don't tell us which. What happened next is where things get interesting, because instead of settling into comfortable middle age, instead of accepting his honours and living quietly, Democritus began to think thoughts that would haunt philosophy for the next 2 millennia. Start with this question. What is everything made of? It seems simple. Look around. You see wood and stone, water and air, flesh and bone. But what are these made of? Can you keep dividing them forever? Or is there a point where you reach something fundamental, something that can't be divided further? The question wasn't new. Philosophers had been arguing about it for a century. Thales had claimed everything was ultimately water. Heraclitus said fire. Empedocles proposed 4 elements: earth, air, fire, and water mixing in different proportions. Anaxagoras suggested that everything contained seeds of everything else, that a piece of bread contained tiny bits of flesh and bone, and blood, which your body separated out during digestion. These were all attempts to solve the same puzzle. The world appears diverse and changing, but is there something permanent beneath the change? Something unchanging that explains why anything exists at all? Democritus, drawing on ideas his teacher Leucippus had begun developing, proposed something radical. Everything is made of atoms and void. That's it. Just 2 things. Atoms, from the Greek word atomos, meaning uncuttable, were tiny particles too small to see. They were solid, indestructible, and eternal. They came in different shapes and sizes, but they were all made of the same fundamental stuff. And between the atoms was void, empty space, nothing at all. Everything you see, everything you touch, everything you are, is just atoms moving through void. They collide, they hook together, they form temporary arrangements that we call objects. But the atoms themselves never change. They've always existed and always will. The universe is infinite in extent and infinite in time. There was no creation, there will be no end. Just atoms, forever, moving through empty space. Your body? Atoms. Your thoughts? Atoms moving in your brain. The gods themselves? If they exist at all, they're made of atoms too. Death? Just the atoms of your body dispersing, returning to the void, ready to form new combinations. This was atheism dressed in philosophical language, and everyone knew it. If the gods are just atoms, they can't be all-powerful. If everything happens through mechanical collisions of particles, there's no room for divine intervention or purpose. If the soul is just a special arrangement of atoms that disperses at death, there's no afterlife, no judgment, no eternal reward or punishment. Other philosophers were horrified. Aristotle, writing a century later, would devote a considerable effort to refuting atomism. Plato apparently disliked Democritus so intensely that he wanted all his books burned. The Stoics developed elaborate arguments against the void, insisting that everything must be continuous, that emptiness was impossible. But here's the remarkable thing. Democritus didn't just propose atoms as a philosophical principle, he tried to explain everything with them. Vision? Atoms fly off objects and strike your eye. Taste? Different shaped atoms interact with your tongue in different ways. Thought? Particularly fine, smooth atoms moving in the soul. Disease? Atoms of the body falling into disorder. Why does honey taste sweet? Because its atoms are smooth and round. Why does vinegar taste sour? Because its atoms are sharp and jagged. Some of these explanations seem absurd now, but the method wasn't absurd. He was trying to explain the observable world through mechanical principles, through the interactions of material particles following natural laws. No magic, no divine intervention, no purpose or intelligence guiding events. Just atoms moving according to their nature. He was doing science. 2,300 years before the scientific revolution, he was already thinking like a scientist. And this brings us to the other aspect of Democritus that made him notorious, the thing that earned him his nickname and puzzled his contemporaries for centuries. He laughed at everything. They called him the laughing philosopher. While Heraclitus had supposedly wept at human folly, Democritus laughed at it. He found the world absurd, human pretensions ridiculous, the whole cosmic drama nothing but atoms colliding in void. Why not laugh? Imagine his perspective for a moment. You've realized that everything people care about is temporary arrangements of particles. Wealth, atoms, power, atoms, glory, atoms, the mighty empire, atoms that will eventually scatter. The beautiful youth, atoms that are already beginning to disperse. Life itself, a brief configuration that time will unmake. Some found this horrifying. If nothing matters, why do anything? Why not just give up? But Democritus drew the opposite conclusion. If nothing is permanent, if everything is temporary, then you might as well enjoy the temporary arrangement you're experiencing now. Pleasure is good, moderation is wise, tranquility is the highest achievement. But none of it is serious. It's all just atoms, and atoms don't care. The laughter wasn't cynical. It was liberation. Once you understand that the universe has no purpose, that everything happens through mechanical necessity rather than divine plan, you're free. Free from fear of the gods, free from anxiety about death, free from the burden of cosmic significance. Just live, observe, think, laugh at the absurdity of existence. And when your atoms finally disperse, well, they'll form something else. The universe will continue. Atoms don't end. But there was a problem with this philosophy, a problem that would haunt Democritus in his old age and eventually contribute to his theory being forgotten for almost 2,000 years. If everything is just atoms moving through void, following mechanical laws, then where does human choice come from? Are we just elaborate machines, our thoughts and decisions as predetermined as the falling of a stone? Democritus never solved this problem. Neither did his followers. And as we'll see, this question would become one of the main reasons why atomism, despite its explanatory power, would eventually lose out to philosophies that preserved human freedom and moral responsibility. But that's a story for later. For now, Democritus was still in his prime, still developing his ideas, still trying to understand how atoms could explain everything from ethics to epistemology. He was about to confront the deepest problem any philosopher can face. If everything is atoms, including our senses, how can we trust what our senses tell us about atoms? The problem hit Democritus like a physical blow. If everything is atoms, including your eyes and brain, then your perceptions are just atoms interacting with other atoms. But atoms can't be trusted. They produce illusions. They show you a world of colour and taste and sound, none of which actually exists in the atoms themselves. Colour is convention, Democritus admitted. Sweetness is convention. Only atoms and void are real. This was deeply troubling. Your entire knowledge of the world comes through your senses. You see the sun, you taste honey, you hear thunder, but Democritus had just argued that these experiences don't correspond to reality. The honey isn't actually sweet. The sun isn't actually bright. These are just how your particular atomic configuration responds to other atomic configurations. So how can you claim to know anything about atoms at all? You learned about atoms through reasoning, sure. But that reasoning started with sensory observations. You watched how things move, how they combine and separate, how they change, all sensory information, all potentially unreliable. The senses themselves fought back. There's a fragment preserved where Democritus imagines the senses speaking to the mind. Wretched mind, you get your evidence from us and yet you try to overthrow us? Our overthrow will be your downfall. It's a striking moment of philosophical honesty. Democritus recognized that his theory had created an internal contradiction. He needed the senses to build his atomic theory, but his atomic theory undermined trust in the senses. He tried to solve this by distinguishing two kinds of knowledge. Genuine knowledge comes from reason. It grasps atoms and void, the true nature of reality. Bastard knowledge comes from the senses. It gives you appearances, conventions, the surface of things. Genuine knowledge is superior, but even Democritus had to admit that genuine knowledge depends on bastard knowledge. To get started, you can't reason about atoms without first observing the world through your senses. This problem would plague atomism for centuries. If you can't trust your senses, why trust the observations that led you to atomism in the first place? Democritus never fully resolved it, but he kept thinking, kept observing, kept trying to explain more and more of reality through atomic motion. He turned his attention to the mind itself. Thought had to be atoms too, but what kind of atoms? His answer was elegant. The soul is made of the finest, smoothest, most mobile atoms, fire atoms essentially. These soul atoms are distributed throughout the body, one soul atom between every few body atoms. They're what give you life, consciousness, the ability to move and think. When you perceive something, atoms from the object strike your sense organs, causing disruptions that travel inward and affect your soul atoms. The particular pattern of disturbance creates your perception. Different patterns create different experiences. This explained why different people perceive things differently. Your atomic configuration is unique. The same external atoms will create different patterns in different souls. It also explained death. When you die, your soul atoms disperse. The fine mobile fire atoms escape into the air. The pattern that was you dissolves. There's no afterlife because there's no permanent you, just atoms that briefly held a particular arrangement. You can see why this wasn't popular. People wanted immortality. They wanted to believe their souls would persist after death, that they would meet their loved ones again, that there would be justice in the afterlife for wrongs unpunished in life. Democritus offered none of that, just dispersal, just atoms returning to the cosmic reservoir to form something else, but he didn't see this as depressing. Death is nothing to us, he argued. When we exist, death is not present. When death is present, we don't exist, so why fear something you'll never experience? This logic would later be developed more fully by Epicurus, but the seed was planted here. Democritus was building an entire worldview on atoms. Physics, biology, psychology, ethics, all explained through the same simple principles. And it was working, mostly. There were problems, of course. His atomic theory couldn't explain everything. Why do some atomic combinations create consciousness, while others don't? What makes the atoms of a living thing different from the atoms of a dead thing? How do memories persist if atoms are constantly moving and rearranging? These questions troubled him. He had answers, but they were incomplete, speculative. He knew it. His critics knew it. And there was a bigger problem looming, one that would eventually prove fatal to atomism's dominance in ancient thought: purpose. Democritus's universe had no purpose. Events happened because atoms collided and hooked together, not because anything was trying to achieve a goal. There was no cosmic plan, no divine intelligence guiding things toward good outcomes, just mechanical necessity. This bothered people deeply. When you look at the world, it seems designed. The eye is obviously for seeing, the ear is obviously for hearing. Seeds obviously intend to become plants, children obviously aim to become adults. How can you explain all this apparent purpose if everything is just atoms blindly colliding? Democritus tried. He argued that what looks like purpose is actually the result of mechanical processes that happen to produce stable, self-perpetuating patterns. The eye works well for seeing, not because it was designed to see, but because eyes that worked well for seeing survived, while eyes that didn't work well disappeared. It's an astonishingly modern argument. He was groping towards something like natural selection, the idea that useful structures emerge through a process of variation and retention rather than design. But he couldn't develop it fully. The mathematics wasn't there. The timescales involved were hard to grasp. And most importantly, it just seemed implausible to his contemporaries that something as intricate as an eye could arise without a designer. Meanwhile, another philosophical tradition was developing in Athens, one that would offer a very different answer to the questions Democritus was wrestling with. This tradition had a name that would echo through history: Platonism, and it was about to change everything. Democritus probably never met Plato. The chronology makes it possible, but unlikely. Plato was born around 428 BCE, when Democritus was already an old man. By the time Plato was establishing his academy in Athens, Democritus would have been dead or very close to it. But Plato knew of Democritus. He had to. Democritus's ideas were circulating throughout the Greek world. His books were being read and discussed. His atomic theory was one of the major philosophical options available to anyone thinking seriously about the nature of reality. And Plato hated it, not openly. Plato never mentions Democritus by name in any of his surviving dialogues. This silence is conspicuous and probably deliberate. Some ancient sources claim that Plato wanted to burn all of Democritus's writings. Whether that's true or exaggerated, it reveals the intensity of the philosophical disagreement. Because everything Plato believed, everything he built his entire system on, was directly contradicted by atomism. Plato believed in eternal, unchanging forms, perfect ideals that existed in a realm beyond the physical world. The form of beauty, the form of justice, the form of the good. These were more real than anything you could touch or see. The physical world was just a pale, imperfect copy of these eternal truths. Democritus said no, there are only atoms and void, no eternal forms, no perfect ideals in another realm, just particles moving through emptiness. Everything you see, including what you call beauty or justice, is temporary arrangements of atoms, nothing more. Plato believed the so. Hic was immortal and immaterial. It existed before birth, it would exist after death, and its true home was the realm of forms. The body was a prison, a distraction from the soul's higher nature. Democritus said no, the soul is atoms, fine atoms, mobile atoms, but still atoms. When the body dies, the soul atoms disperse. There's no immortality, no eternal essence, no escape to a higher realm, just dissolution. Plato believed that knowledge comes from the soul's recollection of the forms it encountered before birth. True understanding means turning away from the deceptive physical world and focusing on eternal truths grasped through pure reason. Democritus said no. Knowledge comes from observing the physical world, even if that observation is limited and sometimes unreliable. There are no eternal forms to recollect. There's only the attempt to understand the patterns of atomic motion through careful reasoning about physical evidence. These weren't minor disagreements. They represented fundamentally incompatible visions of reality, and Plato's vision was gaining ground. Why? The answer is complex, but part of it was that Plato's philosophy preserved what people wanted to believe: immortality, purpose, moral absolutes, the idea that there's something beyond the physical, something higher and better and permanent. Atomism offered none of that. It was austere, mechanical, seemingly nihilistic. Yes, Democritus laughed. Yes, he argued for tranquility and moderation. But his philosophy seemed to leave nothing to aim for, nothing sacred, nothing that ultimately mattered. Plato's philosophy did. It gave you a reason to pursue wisdom, to cultivate virtue, to resist bodily temptations. Because the soul was eternal and its choices had permanent consequences, Platonism also aligned better with religious intuitions. Most Greeks believed in gods, in divine providence, in the idea that the universe was ordered by intelligence. Atomism was effectively atheistic. The gods, if they existed at all, were just configurations of atoms with no power over the cosmic order. Plato's forms, on the other hand, could be integrated with traditional religion. The form of the good could be identified with Zeus or with divine reason. The eternal realm of forms could be understood as the mind of God. This made Platonism much more palatable to the religious mainstream. And there was another factor. Plato founded the Academy, a school that would continue for centuries, training generations of philosophers in the Platonic tradition. These students spread Plato's ideas throughout the Mediterranean world. Democritus had no school. He had admirers, followers, people who read his books and were influenced by his ideas. But there was no institutional structure to preserve and develop atomism after his death. The theory was vulnerable, and then something happened that would doom atomism for nearly 2,000 years. Aristotle arrived. Aristotle was Plato's student. He studied at the Academy for 20 years, absorbing Platonism deeply. But Aristotle was also a brilliant independent thinker who eventually rejected many of Plato's core ideas. He didn't believe in the separate realm of forms. He thought Plato had multiplied entities unnecessarily, creating a whole other world to explain this one. Instead, Aristotle developed his own system, one that kept what he valued from Platonism, the emphasis on purpose and form, while grounding everything firmly in the physical world. No separate realm of forms, just this world, understood through careful observation and logical analysis. You'd think Aristotle's rejection of Plato's forms would help atomism. After all, if there's no separate eternal realm, maybe reality is just atoms moving through void, right? Wrong. Aristotle rejected atomism even more forcefully than Plato did. And because Aristotle became the most influential philosopher in Western history for the next 2 millennia, his rejection was devastating. Aristotle's attack on atomism was systematic and thorough. He developed arguments that seemed to prove atoms were impossible, not just unlikely, impossible. First, the void. Aristotle argued that a true void, an absolute nothing, cannot exist. Why? Because in a void there would be no up or down, no direction at all. Everything would be the same in every direction. So an object in a void would have no reason to move in one direction rather than another. It would remain motionless, but the atomists said atoms move through the void constantly. Aristotle said this was incoherent. Motion requires a medium. An object moves through water differently than through air because water and air resist differently. In a void with no resistance at all, motion would be instantaneous, infinite speed. But infinite speed is impossible. Therefore void is impossible. Therefore atomism is impossible. Second, the infinite divisibility problem. Aristotle argued that matter must be infinitely divisible. You can always, in principle, cut something in half. There's no point where you suddenly can't divide anymore. The atomists said no, eventually you hit something uncuttable. Aristotle said this violated mathematical principles. Space is infinitely divisible, so anything occupying space must also be infinitely divisible. Atoms occupying space but being indivisible is a contradiction. Third, the problem of qualities. How do colourless, tasteless, qualityless atoms create the world of colour, taste, and quality we experience? The atomists said qualities emerge from atomic arrangements. Aristotle said this was absurd. You can't get something from nothing. If atoms have no qualities, arrangements of atoms can't suddenly produce qualities. It's like saying you can build a coloured wall from invisible bricks. Fourth, purpose. This was perhaps Aristotle's deepest objection. The atomists said everything happens by mechanical necessity. Atoms collide, bounce, combine, according to their shapes and motions. There's no purpose, no goal, no reason why. Aristotle found this deeply unsatisfying. When you look at living things, purpose is everywhere. Eyes are for seeing. Hearts are for pumping blood. Acorns are striving to become oak trees. Nature is full of purpose, of things achieving their proper ends. Atomism can't explain this. It can only say these appearances of purpose are illusions, accidents of atomic collision. Aristotle refused to believe that. Instead, he developed his own theory of matter. Not atoms, but 4 elements: earth, water, air, fire. These aren't indivisible particles. They're continuous substances that can transform into each other. Earth can become water, water can become air, air can become fire, and vice versa. Everything in the world is made from combinations of these 4 elements in various proportions. More importantly, Aristotle said that objects have inherent tendencies. Earth naturally moves downward toward the centre of the universe. Fire naturally moves upward. Objects don't move because atoms are bouncing around. They move because they're seeking their natural place in the cosmic order. This theory was wrong. Completely, fundamentally wrong. But it made intuitive sense. Heavy things do fall down. Fire does rise. You drop a rock, it falls. You light a fire, the flames go up. Aristotle's explanation seemed to fit the evidence better than atomism's claim that everything is just particles moving in void. And Aristotle's system preserved what people wanted: purpose, order, intelligence in nature. The idea that the universe is rational and comprehensible. Atomism threatened all of that. It made the universe seem random, purposeless, mechanical. So when Aristotle's works were rediscovered in medieval Europe and became the foundation of university education, atomism was buried even deeper. For more than 1,000 years, from roughly 300 CE to 1600 CE, atomism was nearly forgotten in the Western world. Democritus's books were lost. His ideas survived only in fragments, in quotations by his critics, in brief mentions by later writers who disagreed with him. The irony is bitter. Democritus had been right about so much. Matter is made of tiny indivisible particles. The soul is physical, not eternal. The universe operates by natural law, not divine whim. These insights, achieved through pure reasoning in the 5th century BCE, were dismissed and forgotten. And when they were finally rediscovered in the Renaissance, scientists had to fight the same battles all over again. They had to argue against Aristotle's 4 elements. They had to prove that void could exist. They had to demonstrate that matter is made of particles. It took 2,000 years for atomism to return from exile. But before we get to that resurrection, we need to understand what happened to Democritus's ideas in the immediate aftermath of his death. Because one group did preserve atomism. One philosophical school kept the atomic flame burning, even as Platonism and Aristotelianism dominated the mainstream. That school was Epicureanism, and its founder Epicurus would transform Democritus's abstract physics into a practical philosophy of how to live. Epicurus was born in 341 BCE on the island of Samos. He was 18 when Alexander the Great died. He came of age in a world that was transforming rapidly, where old certainties were dissolving, where Greek city-states were being absorbed into vast empires. People wanted answers, not just about physics, but about how to find happiness in an uncertain world. Epicurus found those answers in atomism. He embraced Democritus's basic theory. Everything is atoms and void. The soul is atomic and mortal. The gods, if they exist, are distant and unconcerned with human affairs. But Epicurus made one crucial modification. Democritus said, atoms move in strict mechanical necessity. Every collision, every combination is determined by prior causes, stretching back infinitely. Epicurus found this determinism troubling. If everything is predetermined, how can humans have free will? How can we be morally responsible for our actions? His solution was the swerve. Epicurus proposed that atoms occasionally deviate slightly from their paths without any cause. Just a tiny random swerve. This breaks the chain of determinism and creates room for free will. Modern physicists would call this quantum indeterminacy, though Epicurus knew nothing of quantum mechanics. He simply needed a way to preserve human agency in an atomic universe. But Epicurus's real contribution wasn't physics, it was ethics. He took Democritus's cheerfulness, his emphasis on tranquility, and built an entire philosophy of life around it. The goal of life, Epicurus said, is pleasure, not wild hedonism, not drunken orgies and constant indulgence. That's a misunderstanding that has plagued Epicureanism for 2,000 years. Epicurus meant something much more subtle. The highest pleasure is the absence of pain, physical comfort and mental tranquility, ataraxia, calm. Most people chase after things that ultimately make them unhappy. Wealth, fame, power, luxury. These pursuits bring anxiety, competition, fear of loss. They disturb your peace. Epicurus said, simplify. Live modestly. Surround yourself with friends. Study philosophy. Understand the nature of reality so that superstitious fears don't torment you. Fear of death? Unnecessary. Death is just the dissolution of your atomic structure. You won't experience it. As Epicurus famously said, death is nothing to us. When we exist, death is not present. When death is present, we do not exist. Fear of the gods? Unnecessary. The gods exist, Epicurus believed, but they're made of atoms like everything else. They live in peaceful contemplation in the spaces between worlds. They don't care about human affairs. They don't punish or reward. They're not watching you. Fear of fate? Unnecessary. The atomic swerve means nothing is absolutely predetermined. You have agency. Your choices matter. This was liberation. For people living in a world of constant anxiety, religious superstition, and political chaos, Epicureanism offered a way out. Understand the physics, live simply, cultivate tranquility. Epicurus founded a school in Athens called the Garden. Unlike Plato's Academy or Aristotle's Lyceum, the Garden was a refuge, a community of friends living according to Epicurean principles. Women were admitted, unusual for ancient philosophical schools. Slaves were admitted. The Garden was radically egalitarian, and it lasted. For centuries, Epicurean communities spread throughout the Mediterranean world. They kept atomism alive when it was under attack from Platonists and Aristotelians. They preserved Democritus's insights and added their own refinements. The greatest Epicurean text that survives is not by Epicurus himself, but by a Roman poet named Lucretius. In the 1st century BCE, Lucretius wrote a long philosophical poem called De Rerum Natura, On the Nature of Things. It's one of the masterpieces of Latin literature, 6 books of poetry explaining atomic theory and its implications for how to live. Lucretius wasn't writing for specialists. He was writing for the general educated public. He wanted to free people from a religious fear. He described atomic motion, explained how worlds form and dissolve, showed how the soul is mortal and death is nothing to fear. His goal was therapeutic, philosophy as medicine for the anxious soul. The poem is beautiful, passionate, sometimes surprisingly modern. Lucretius describes atoms in language that anticipates later scientific discoveries. He talks about how nothing can come from nothing, a principle that would become fundamental in physics. He explains that atoms are in constant motion, even in seemingly solid objects. He describes how sensory perception works, how images stream off objects and strike our eyes. Much of this is wrong in detail, but the underlying approach trying to explain everything through atoms and void is remarkably sound. But here's the tragedy. Even as Epicureanism was spreading, even as Lucretius was writing his masterpiece, the tide was already turning against atomism. Rome was rising, and Rome would eventually embrace not Epicureanism, but Stoicism and Platonism. Christianity was coming. And Christianity had no use for a philosophy that denied the immortal soul and the active involvement of God in human affairs. By the 4th century CE, Epicureanism was in decline. By the 6th century, it was effectively extinct. The garden closed, the communities dissolved, the books were lost or destroyed. Lucretius's poem survived, but barely. Only a handful of medieval manuscripts preserved it. If those had been lost, we would know almost nothing about Epicurean atomism in any detail, and for 1,000 years, atomism was dead. Not just unpopular, not just out of fashion, dead. The idea that matter is made of atoms was considered heretical, atheistic, dangerous. Universities taught Aristotle. The church endorsed Aristotle. 4 elements: natural place, purpose in nature. That was the official doctrine. Democritus, the laughing philosopher who saw through to the atomic structure of reality, was forgotten. His books were gone. His name appeared only in hostile summaries by Christian writers who used him as an example of pagan foolishness. The darkness lasted roughly from 500 CE to 1500 CE, a millennium, but knowledge has a way of resurfacing. Books that were lost get found. Ideas that were buried get excavated. And in the 15th century, something remarkable happened. A manuscript hunter named Poggio Bracciolini was searching through a German monastery library in 1417. He was looking for classical texts that had been copied by medieval monks and then forgotten. Most of what he found was religious material. But then he discovered something extraordinary, a copy of Lucretius, De Rerum Natura, complete, all 6 books. Poggio couldn't read it there. He had to copy it by hand, a months-long process. But he did, and that copy made its way to Italy. And then more copies were made, and then it was printed. And suddenly, After 1,000 years of silence, Epicurean atomism was back. The timing was perfect. Europe was in the midst of the Renaissance. Ancient learning was being recovered and celebrated. The authority of Aristotle was being questioned. Scientists were beginning to conduct experiments, to observe nature carefully rather than just citing ancient authorities. And here was Lucretius, describing a universe of atoms and void, operating by natural law, with no divine intervention required. It was shocking. It was dangerous. It was also thrilling. The recovery of Lucretius changed everything. It gave Renaissance thinkers an alternative to Aristotle. It provided a framework for thinking about matter that didn't depend on purpose or final causes. It suggested that the universe might be fundamentally mechanical, and slowly, over the next 2 centuries, atomism began its comeback. Not quickly, not easily. The church was still powerful. Heresy was still dangerous, but scientists began experimenting with atomic ideas. They began wondering whether maybe, just maybe, Democritus had been right all along. The man who would bring atomism back from the dead wasn't a philosopher. He was a gardener's son from Lincolnshire who dropped out of university and spent years grinding lenses in his spare time. His name was Robert Boyle. Boyle was born in 1627 into extraordinary wealth. His father was the Earl of Cork, one of the richest men in Britain. Young Robert could have spent his life in aristocratic leisure. Instead, he became obsessed with what he called experimental philosophy. We would call it chemistry. He built a laboratory. He hired assistants. He purchased equipment. And he began systematically testing how matter behaves. Not by reading Aristotle, not by logical deduction, by actual observation. His most famous experiments involved air. Using a newly invented air pump, Boyle showed that air has weight, that it exerts pressure, that it can be compressed. He demonstrated that sound doesn't travel in a vacuum, that flames go out without air, that animals die without air. These seem like obvious facts now. They weren't obvious then. But Boyle went further. He argued that air itself must be made of particles, tiny invisible particles with space between them. That's why air could be compressed. You're squeezing the particles closer together. That's why it exerts pressure. The particles are constantly bouncing around, hitting the walls of their container. This was atomism. Not the poetic atomism of Lucretius, but atomism grounded in experimental evidence. Boyle didn't call them atoms, though. He called them corpuscles, little bodies. The terminology mattered. Atoms carried too much philosophical baggage, too many associations with atheism and Epicureanism. Corpuscles sounded more respectable, more scientific. But the idea was the same. Matter is made of tiny, indivisible particles. Everything we observe, all the properties of substances, can be explained by the size, shape, and motion of these particles. He published his ideas in 1661 in a book called The Skeptical Chymist. It attacked the old Aristotelian theory of 4 elements. It proposed instead a corpuscular philosophy of matter, and it helped launch what historians call the scientific revolution. Boyle wasn't alone. Across Europe, natural philosophers were converging on similar ideas. In France, Pierre Gassendi had already rehabilitated Epicureanism, arguing that atomic theory could be separated from its atheistic implications. You could believe in atoms and still believe in God. The atoms themselves could be God's creation. This was crucial. It made atomism theologically acceptable. You didn't have to be an atheist to think matter was made of particles. In Italy, Galileo had described matter as composed of infinitely small particles, though he was careful not to develop the idea too far. The Inquisition was watching. And in England, Isaac Newton was about to take corpuscular philosophy to its ultimate conclusion. Newton is famous for his laws of motion and his theory of gravity. Less famous but equally important was his corpuscular theory of light. He argued that light consists of streams of particles, corpuscles, travelling through space and bouncing off objects. He was half right. Light behaves like particles in some experiments and like waves in others. But Newton's corpuscular theory dominated for a century. More importantly, Newton showed that the entire universe operates according to mathematical laws. The same force that makes an apple fall makes the planets orbit the sun. Nature is comprehensible. Nature is predictable. Nature is mechanical. This was the Newtonian synthesis, and at its foundation was the idea that matter is made of particles interacting according to fixed laws. Democritus had imagined it. Lucretius had described it. Now Newton had proved it, or so it seemed. But here's the thing about atoms in the 17th and 18th centuries. Nobody had ever seen one. Nobody could measure one. Nobody could prove they existed. The evidence was indirect. Air behaves as if it's made of particles. Chemical reactions work as if matter combines in fixed ratios. Light travels as if it's a stream of corpuscles. As if. Some philosophers weren't convinced. They argued that atoms were a useful fiction, a way of thinking about matter, but not necessarily real physical entities. Maybe matter is infinitely divisible. Maybe there's no smallest piece. The debate raged for another century, and the answer wouldn't come from philosophy. It would come from a Quaker schoolteacher in Manchester who spent his evenings measuring gases. John Dalton was born in 1766 in a small village in Cumberland. His family was poor. His education was limited. He became a teacher at age 12, teaching students who were almost as old as he was. He was largely self-taught. He read everything he could find about mathematics and natural philosophy. He kept meticulous weather records, making observations every day for 57 years. He was obsessed with measurement, with precision, with finding patterns in data. In 1793, he moved to Manchester to teach mathematics at a dissenting academy. Dissenters were Protestants who rejected the Church of England. They couldn't attend Oxford or Cambridge. They built their own schools, and those schools, ironically, often provided better scientific education than the ancient universities. Dalton began experimenting with gases. He wanted to understand why different gases behave the way they do. Why does oxygen have a different density than nitrogen? Why do gases mix in certain proportions? He discovered something remarkable. When gases combine chemically, they always combine in simple whole number ratios. If you make water from hydrogen and oxygen, you always need exactly 2 volumes of hydrogen for every 1 volume of oxygen. Exactly 2 to 1. Never 2.1 to 1. Never 1.9 to 1. Always exactly 2. Why? Dalton realized there was only one possible explanation. Matter must be made of indivisible particles, atoms, and each element must have its own characteristic type of atom. A hydrogen atom, an oxygen atom, a nitrogen atom. When elements combine, the atoms join together in simple ratios. Water is 2 hydrogen atoms bonded to 1 oxygen atom. That's why the ratio is always exactly 2 to 1. You can't split an atom. You can't have half a hydrogen atom. The ratios must be whole numbers because atoms are whole units. This was the breakthrough. This was the empirical evidence that atomism needed. Dalton published his atomic theory in 1808 in a book called A New System of Chemical Philosophy. He proposed that each element consists of identical atoms with a specific weight. He even calculated relative atomic weights for different elements. He was wrong about many details. He thought water was HO, not H2O. He didn't understand that many gases exist as paired atoms, molecules. He couldn't explain why atoms bond the way they do. But the core insight was correct. Matter is made of atoms. Different elements have different atoms. Chemical reactions are just atoms rearranging themselves. The scientific community was skeptical at first. The evidence was indirect. The theory was radical. And Dalton himself was an outsider. a provincial teacher with no university credentials. But the evidence kept accumulating. Other chemists repeated Dalton's experiments and got the same results. The law of definite proportions held across countless chemical reactions. The atomic theory explained so much, predicted so much, unified so much. By the 1850s, most chemists accepted that atoms were real, not just useful fictions, real physical entities. But questions remained, big questions. What are atoms made of? Why do they have the properties they do? How do they bond together? Are they truly indivisible, or do they have internal structure? The answers would require new tools, new mathematics, new ways of seeing. The 19th century would bring all of that, and it would reveal that atoms, far from being the smallest things, are entire universes unto themselves. But we're getting ahead of ourselves. Let's pause here at the moment of triumph, 1850. 2,000 years after Democritus first proposed that matter is made of uncuttable particles, science had finally caught up with philosophy. The atomists had been vindicated, but the story was far from over. In fact, it was only beginning. Because while chemists were celebrating the atomic theory, physicists were about to tear it apart. Not to disprove it, but to look inside, to find structure where none was supposed to exist, to discover that the uncuttable can be cut after all. The first hint came from electricity. In the 1830s, Michael Faraday discovered that when you pass an electric current through certain liquids, the liquid decomposes in precise proportions. Just like Dalton's gases, the amounts of different substances produced are always related by simple whole number ratios. Faraday proposed that electricity itself might be atomic. That just as matter comes in discrete units called atoms, electric charge might come in discrete units too. He didn't have a name for these units. Later scientists would call them electrons. But Faraday's insight was profound. If electricity is atomic, and electricity can be separated from matter, then maybe atoms aren't the smallest things after all. Maybe they have parts. Nobody pursued this idea immediately. The technology wasn't ready. The mathematics wasn't ready. The conceptual framework wasn't ready. But by the 1890s, everything changed. Physicists developed something called a cathode ray tube. It's a glass tube with the air pumped out and two metal plates inside. When you apply a high voltage, a mysterious ray shoots from one plate to the other. You can see it glow in the darkness. What is this ray? Is it light? Is it some kind of wave? Is it matter? Experiments showed that the ray could be deflected by a magnet. That suggested it was made of charged particles, not light. Other experiments showed it could be deflected by an electric field. More evidence for particles. In 1897, J.J. Thomson at Cambridge performed the definitive experiment. He measured how much the rays bent in electric and magnetic fields. From that, he could calculate the mass-to-charge ratio of whatever was producing the rays. The result was shocking. Whatever these particles were, they were incredibly light, nearly 2,000 times lighter than a hydrogen atom, the lightest atom known. Thomson had discovered the electron, a particle of matter smaller than an atom. A piece of an atom. The uncuttable had been cut. This changed everything. If atoms contain electrons, then atoms have internal structure. They're not indivisible after all. They're complex systems with parts that can be separated and studied. Thomson proposed a model. He suggested that atoms are like plum pudding, a sphere of positive charge with electrons embedded in it like raisins in a pudding. The positive and negative charges balance out, making the atom electrically neutral overall. It was a reasonable guess. It was also completely wrong. The correct model would emerge from a series of experiments conducted in a basement laboratory in Manchester by a scientist from New Zealand who would become one of the greatest experimentalists of all time. His name was Ernest Rutherford, and he was about to discover something that would make Thomson's plum pudding look like a child's toy. Rutherford was studying radioactivity. he discovered that radioactive materials emit different types of radiation, which he called alpha, beta, and gamma rays. Alpha rays turned out to be helium nuclei. Beta rays were electrons. Gamma rays were high-energy light. In 1909, Rutherford decided to use alpha particles as probes. He would fire them at a thin sheet of gold foil and see what happened. If Thomson was right, if atoms were soft puddings of positive charge with electrons scattered throughout, then the alpha particles should pass straight through with only slight deflections. Like bullets through fog, most of them did, but some didn't. Some bounced back. A few even bounced straight back toward the source. Rutherford was astounded. He later said it was as if you fired a cannonball at tissue paper and it bounced back and hit you. There was only one possible explanation. The positive charge in an atom isn't spread out. It's concentrated in a tiny, dense nucleus at the center. Most of the atom is empty space. The electrons orbit the nucleus like planets orbiting the sun. When an alpha particle hits the nucleus head-on, it bounces back. When it misses, it sails through the empty space. This was the nuclear model of the atom, and it was revolutionary. Atoms aren't solid spheres. They're mostly nothing. A tiny nucleus surrounded by a vast empty space where electrons somehow orbit. But there was a problem. If electrons orbit the nucleus like planets orbit the sun, then according to the laws of physics that had been established, they should radiate energy constantly. An orbiting electron is an accelerating charge, and accelerating charges emit electromagnetic radiation. That's not speculation. That's Maxwell's equations. And if the electron radiates energy, it loses energy, which means it should spiral inward toward the nucleus, fast. The calculation is straightforward. An electron orbiting a nucleus should collapse within a fraction of a second. Every atom in the universe should self-destruct almost instantly. But they don't. You exist, I exist, the chair you're sitting on exists. Atoms are stable. Something is wrong with the calculation, or something is wrong with the laws of physics. Enter Niels Bohr. In 1913, a young Danish physicist arrived at Rutherford's lab in Manchester. Bohr had been thinking about atoms, about electrons, about the strange stability that shouldn't exist. He proposed something radical. What if electrons can only exist in certain specific orbits? Not just any distance from the nucleus, but only particular, allowed orbits, like steps on a ladder. You can stand on the first step or the second step, but you can't stand halfway between. There is no halfway. In these special orbits, Bohr proposed, the electron doesn't radiate, it just stays there, stable, defying what classical physics says should happen. Why? Bohr didn't have a deep explanation. He just said, this is what must be true if atoms are going to exist at all. He built his model backward from the requirement that atoms be stable, but here's what made the Bohr model brilliant. It explained something that had puzzled scientists for decades. When you heat an element until it glows, it doesn't emit all colours of light. It emits specific colours. Hydrogen glows with particular shades of red, blue-green and violet. Not a smooth spectrum, but discrete lines. Sodium produces a characteristic yellow. Neon gives off red-orange. Each element has its own unique spectral fingerprint. Scientists had been cataloguing these spectral lines since the 1850s. They'd even found mathematical patterns in them, but nobody understood why atoms behaved this way. Why discrete lines instead of continuous colours? Bohr's model explained it perfectly. If electrons can only exist in specific orbits, then they can only have specific energies. When an electron drops from a higher orbit to a lower one, it releases energy in the form of light. But since the orbits are quantized, the energy differences are quantized, which means the light comes out in specific colors, specific wavelengths. Each jump produces one spectral line. The model predicted the exact wavelengths of hydrogen's spectral lines with stunning accuracy. Bohr had cracked the code, but the model was strange. Why should electrons be restricted to certain orbits? What physical principle enforces that rule? Bohr couldn't say. He'd created a model that worked, but it felt incomplete, like a house built without proper foundations. And there were problems. The Bohr model worked beautifully for hydrogen. One electron orbiting one proton. Simple. But when you tried to apply it to helium with 2 electrons, the calculations became messy. For anything more complex, the model broke down entirely. Something deeper was needed. That something would arrive in 1924 from an unexpected source. A French graduate student named Louis de Broglie was writing his doctoral thesis. He had an idea so strange that his thesis committee almost rejected it. Einstein had shown that light, which everyone thought was a wave, sometimes behaves like a particle. Photons, discrete packets of energy. De Broglie asked the opposite question. If waves can behave like particles, can particles behave like waves? Specifically, could electrons be waves? It sounds absurd. An electron is a thing. A tiny ball of matter with mass and charge. How can a thing be a wave? But de Broglie worked out the mathematics. If an electron has momentum, and if you assign it a wavelength using a simple formula, everything starts to make sense. The formula is elegant. The formula is wavelength equals Planck's constant divided by momentum. That's it. For large objects, the wavelength is so incredibly small that it's irrelevant. You're not a wave in any meaningful sense. But for something as tiny as an electron, the wavelength is significant. And here's the key insight. If an electron is a wave, then the reason only certain orbits are allowed becomes obvious. Imagine a wave traveling in a circle. For the wave to be stable, the circumference of the circle must be an exact multiple of the wavelength. 1 full wavelength fits around the circle, or 2, or 3, but not 1.5. That would mean the wave interferes with itself destructively, cancelling out. Only certain orbits allow stable waves. Those are the Bohr orbits. De Broglie's thesis committee was skeptical. They sent his work to Einstein, asking what he thought. Einstein read it and declared it brilliant. De Broglie got his doctorate. But was it true? Could you actually detect these electron waves? In 1927, 2 American physicists, Clinton Davison and Lester Germer, were studying how electrons bounce off metal surfaces. They fired a beam of electrons at a nickel crystal and observed the pattern of scattered electrons. What they found was interference. The electrons didn't scatter randomly. They created a pattern of bright and dark regions, exactly like light waves passing through a diffraction grating. Electrons are waves. Around the same time, a British physicist named George Paget Thomson, son of J.J. Thomson, who discovered the electron, performed a different experiment that showed the same thing. The irony was perfect. Father proves the electron is a particle. Son proves it's a wave. Both won Nobel Prizes, but calling an electron a wave creates new problems. What exactly is waving? With water waves, water moves up and down. With sound waves, air pressure oscillates. With light waves, electromagnetic fields oscillate. But with an electron wave, what physical quantity is oscillating? The answer came from Austria, from a physicist named Erwin Schrödinger. In 1926, Schrödinger wrote down an equation. It's now simply called the Schrödinger equation, and it's the foundation of quantum mechanics. The equation describes how the electron wave changes over time, but Schrödinger himself wasn't sure what the wave represented. He thought maybe the electron was somehow spread out, smeared across space, a cloud of charge. That interpretation didn't work. The correct interpretation came from a German physicist named Max Born. What Schrödinger's wave describes, Born realized, is not the electron itself. It's probability. The wave function tells you where the electron is likely to be found if you look for it. Where the wave is large, the probability is high. Where it's small, the probability is low. Where it's 0, you'll never find the electron there. This is profoundly weird. Before you measure, the electron doesn't have a definite position. It exists in a superposition of all possible positions, weighted by probability. The wave function describes this state of quantum limbo. When you measure the electron's position, the wave function collapses. All the possibilities vanish except one. The electron appears at a specific location, but which location is fundamentally random. You can calculate the odds, but you can't predict the outcome with certainty. God plays dice. Einstein hated this. He spent the rest of his life arguing that quantum mechanics must be incomplete, that there must be hidden variables determining the outcome. But experiment after experiment confirmed that quantum mechanics is right. The universe is probabilistic at its core. Schrödinger's equation works. It predicts the energy levels of atoms with perfect accuracy. It explains chemical bonding. It underlies all of modern electronics, but it replaces the comforting mechanical universe of Newton with something stranger. And there's more strangeness to come. Around the same time Schrödinger was developing his wave mechanics, a young German physicist named Werner Heisenberg was taking a completely different approach. Heisenberg didn't like waves. He didn't trust models of atoms with little electrons orbiting like planets. He thought physicists should only talk about things they can actually measure. You can measure the light an atom emits. You can measure energies and frequencies. You can't see the electron itself. So why pretend you know what it's doing between measurements? Heisenberg built a new mechanics based purely on observable quantities. He represented physical properties as arrays of numbers, mathematical objects called matrices. The mathematics was abstract, almost algebraic, and buried in that mathematics was something shocking. When Heisenberg tried to calculate both the position and momentum of an electron simultaneously, he found he couldn't. The more precisely you know where an electron is, the less precisely you can know how fast it's moving, and vice versa. This isn't a limitation of measurement technology, it's a fundamental property of nature. The uncertainty principle says that position and momentum are complementary. You can know one or the other to arbitrary precision, but never both at once. The product of the uncertainties has a minimum value. Planck's constant divided by 4 pi. For large objects, this minimum is so small it's irrelevant. But for electrons, it's everything. An electron confined to a small region has uncertain momentum, which means it has kinetic energy even when it's supposedly at rest. This is called zero-point energy, and it prevents atoms from collapsing. The uncertainty principle is why matter is stable, why you don't fall through your chair, why chemistry works. Heisenberg's matrix mechanics looked completely different from Schrödinger's wave mechanics. They were developed independently, based on different philosophies, but when mathematicians analysed them, they discovered something remarkable. They're the same theory. Schrödinger's equation and Heisenberg's matrices are two different mathematical representations of the same underlying physics. You can translate between them. They make identical predictions. This is quantum mechanics, a theory that describes nature in terms of probabilities and uncertainties, a theory where particles are also waves, where nothing has definite properties until you measure it, where the act of observation changes what you observe. It's the most successful scientific theory ever created. Every prediction it's made has been confirmed. Every technology based on it works. Computers, lasers, MRI machines, solar panels, nuclear reactors. The modern world runs on quantum mechanics, but nobody really understands it. Niels Bohr, who became the philosopher king of quantum mechanics, developed what's called the Copenhagen interpretation. It says that quantum mechanics is complete. There's nothing beneath the wave function. The probabilities are fundamental. The universe is indeterminate until you look at it. Einstein rejected this. He believed in an objective reality that exists whether or not you observe it. He and Bohr argued for decades, conducting thought experiments, trying to find flaws in quantum mechanics. Einstein never won those arguments. But here's what's strange. The equations work. The predictions are perfect. But ask 10 physicists what quantum mechanics means. what it says about reality, and you'll get 10 different answers. Some follow Bohr and say the wave function is all there is. Others believe in hidden variables that we haven't discovered yet. Still others think every quantum measurement causes the universe to split into multiple branches, each outcome occurring in a different parallel world. The many worlds interpretation. Every time a quantum event happens, reality branches. You exist in countless parallel universes, experiencing every possible outcome. It sounds like science fiction, but the mathematics supports it. We don't know which interpretation is correct. We may never know. Quantum mechanics works whether or not we understand what it means. And that brings us back to atoms. The Rutherford model said atoms have nuclei. Bohr added quantized orbits. De Broglie made electrons into waves. Schrödinger described them with equations. Heisenberg added uncertainty, but what's actually inside the nucleus? Rutherford had shown it's tiny and dense. But what's it made of? Protons, certainly. Positively charged particles. Hydrogen has 1. Helium has 2. Carbon has 6. The number of protons determines which element you have. But there's a problem. The masses don't add up. A helium nucleus has 2 protons. Each proton weighs about 1 atomic mass unit. So helium should weigh 2 units, but it weighs 4. Carbon has 6 protons. Should weigh 6 units. Actually weighs 12. Every nucleus is roughly twice as heavy as its protons alone would explain. Something else is in there. Rutherford suspected neutral particles. Particles with mass but no charge. He called them neutrons, but nobody could find them. The problem was detection. Charged particles are easy to spot. They ionize atoms as they pass through matter, leaving trails you can see in cloud chambers or record with Geiger counters. Neutral particles leave no trail. They're invisible. In 1930, 2 German physicists, Walther Bothy and Herbert Becker, were bombarding beryllium with alpha particles. They detected strange radiation coming out. Very penetrating radiation that passed through lead. They thought that it was gamma rays, high-energy light, but the properties were odd. This radiation could knock protons out of paraffin wax with tremendous energy. More energy than gamma rays should transfer. The numbers didn't work. In 1932, Irène Joliot-Curie, Marie Curie's daughter, and her husband, Frédéric Joliot-Curie, repeated the experiment. They confirmed the strange radiation. They also thought it was gamma rays, but they couldn't explain the energy. James Chadwick, working in England, heard about these experiments. He knew immediately what was happening. This wasn't electromagnetic radiation. These were neutral particles, neutrons, particles with roughly the same mass as protons, but no electric charge. They could pass through matter easily, because they don't interact electromagnetically. They only interact through the strong nuclear force, which has incredibly short range. Chadwick designed experiments to prove it. He measured the mass by studying collision dynamics. When the mysterious radiation hit hydrogen, it knocked protons forward. When it hit nitrogen, it knocked nitrogen nuclei forward. From the energy transfer, you could calculate the mass of the incoming particle. It matched a proton almost exactly. The neutron was real, and suddenly atomic structure made sense. Nuclei contain protons and neutrons. Protons provide positive charge. Neutrons add mass without adding charge. Hydrogen has 1 proton, no neutrons. Helium has 2 protons, 2 neutrons. Carbon has 6 protons, 6 neutrons. The number of protons determines the element. The number of neutrons can vary. Same element, different masses. These are called isotopes. Carbon-12 has 6 neutrons. Carbon-14 has 8. Both are carbon because both have 6 protons. But carbon-14 is heavier and radioactive. This is what carbon dating uses. Now we had the complete picture. Atoms have nuclei made of protons and neutrons. Electrons orbit in quantum clouds described by Schrödinger's equation. Chemistry happens because electrons interact. Nuclear reactions happen when you change the nucleus itself. But this created a new mystery. Why doesn't the nucleus explode, pack protons together in a tiny space? They're all positively charged. Electromagnetic force should blow them apart instantly. The repulsion should be enormous. Yet nuclei hold together. Something must be holding them. Something stronger than electromagnetism. Physicists called it the strong nuclear force. It's attractive. It only works at incredibly short distances, about the size of a proton. But within that range, it's the strongest force in nature. It overpowers electromagnetic repulsion and binds protons and neutrons together. Neutrons help stabilize the nucleus. They add strong force attraction without adding electromagnetic repulsion. That's why larger nuclei need more neutrons than protons. The ratio shifts. Light elements have roughly equal numbers. Heavy elements need excess neutrons to stay stable. But there are limits. Make a nucleus too large, add too many protons, and no amount of neutrons can hold it together. The electromagnetic repulsion wins. The nucleus becomes unstable. It decays. This is radioactivity. Some nuclei are inherently unstable. They spontaneously break apart, releasing particles and energy. Uranium-238 has 92 protons and 146 neutrons. It's barely holding together. Eventually it spits out an alpha particle, 2 protons and 2 neutrons bound together. What's left is thorium-234, which is also unstable, which decays into something else. A chain of decay that continues until you reach lead-206, which is stable. This is a decay chain. Each step has a half-life, the time it takes for half the atoms to decay. Uranium-238 has a half-life of 4.5 billion years. Other isotopes decay in seconds. This is how we date rocks, how we know the age of the Earth, how we understand geological time. By the mid-1930s, physics seemed nearly complete. Atoms were understood. Quantum mechanics explained chemistry. Relativity explained gravity and motion. A few details remained, but the framework was solid. Then came the discovery that broke everything open. In 1938, Otto Hahn and Fritz Strassmann in Berlin were bombarding uranium with neutrons. They expected to create heavier elements. Instead, they found barium, an element with 56 protons. Uranium has 92 protons. Where did barium come from? Lise Meitner, Hahn's former colleague, who had fled Nazi Germany, worked out the answer with her nephew, Otto Frisch. The uranium nucleus wasn't just chipping off a few particles, it was splitting in half. Nuclear fission. A neutron hits uranium-235. The nucleus absorbs it, becomes unstable, and tears itself apart. It splits into 2 lighter nuclei plus several free neutrons, and it releases energy, enormous energy. Einstein's equation E equals mc squared explained it. The mass of the fragments is slightly less than the mass of the original uranium atom. That missing mass becomes energy. A tiny amount of mass converts to a staggering amount of energy because the speed of light squared is huge. 1 kilogram of uranium-235, if you could fission every atom, releases as much energy as burning 2.5 million kilograms of coal. The energy density is incomprehensible, but there was something else. Each fission releases neutrons, 2 or 3 per split. Those neutrons can hit other uranium atoms, causing them to fission, releasing more neutrons. This is a chain reaction. 1 fission triggers 2. Those trigger 4, 4 trigger 8. The reaction grows exponentially. If you have enough uranium in a smaller nucleus, H space, the chain reaction runs away. In milliseconds, trillions of atoms split. The energy release is catastrophic. This is an atomic bomb. The physics was understood by 1939. The engineering would take 6 years, and the largest scientific project in history. The Manhattan Project? But that's another story. What matters for understanding atoms is this. The nucleus isn't just a lump of protons and neutrons. It's a barely controlled explosion held together by the strong force. And when you disturb it the right way, you unleash the energy that powers stars, because that's where this all happens naturally, inside stars. The sun doesn't burn like fire. Fire is a chemical reaction, electrons rearranging between atoms. The sun fuses nuclei. The core is so hot, so dense, that hydrogen nuclei slam together hard enough to overcome their electromagnetic repulsion and fuse into helium. 4 hydrogen nuclei, 4 protons, become 1 helium nucleus, 2 protons and 2 neutrons. The mass of helium is slightly less than 4 hydrogen. That missing mass becomes energy. The sun converts 600 million tons of hydrogen into helium every second. It loses 4 million tons of mass per second, turned into light and heat. It's been doing this for 4.6 billion years. It will continue for another 5 billion. This is stellar nucleosynthesis. All the heavy elements were forged in stars. The carbon in your body, the calcium in your bones, the iron in your blood. All of it was created in the core of a star that exploded before the sun was born. We are literally made of stardust, not metaphorically, literally. Every atom heavier than helium came from a star. When massive stars exhaust their fuel, they collapse and explode in supernova. The explosion creates temperatures and pressures high enough to fuse elements all the way up to uranium. Those elements scatter through space. They become part of new clouds of gas and dust. Those clouds collapse to form new stars and planets. Our solar system formed from the debris of previous stars. The atoms in your body have been through multiple stars. They're billions of years old, recycled through cosmic furnaces. When you look at the periodic table, you're looking at a history of the universe. Hydrogen and helium were created in the Big Bang. Everything else was built by stars. By the 1950s, physicists understood atoms completely, or so they thought. Electrons orbit nuclei in quantum clouds. Nuclei contain protons and neutrons. The strong force holds nuclei together. Electromagnetism governs chemistry. Gravity shapes the cosmos. 4 fundamental forces. 3 types of particles. A clean, elegant picture. Then they started smashing particles together at higher energies. And the clean picture shattered into hundreds of pieces. Cosmic rays, high-energy particles from space, constantly bombard Earth. When they hit the atmosphere, they create showers of particles. Physicists built detectors. They found particles that shouldn't exist. Particles heavier than electrons but lighter than protons. Particles that appeared and disappeared in microseconds. Strange particles that behaved unlike anything predicted. In 1947, a particle called the muon was discovered. It's like an electron but 200 times heavier. Why does it exist? Nobody knows. It decays into an electron in 2 microseconds. It seems to serve no purpose. Physicists built particle accelerators, machines that accelerate protons or electrons to nearly light speed and smash them together. The collisions create new particles, hundreds of them. Particles with strange properties, particles that exist for billionths of a second. The particle zoo exploded. By the 1960s, physicists had discovered hundreds of supposedly fundamental particles. Too many to be fundamental. There had to be an underlying pattern. Murray Gell-Mann and George Zweig independently proposed that protons and neutrons aren't fundamental. They're made of smaller particles called quarks. Protons contain 3 quarks, 2 up quarks and 1 down quark. Neutrons contain 1 up quark and 2 down quarks. Quarks have fractional electric charge. Up quarks have positive 2/3. Down quarks have negative 1/3. Combine them correctly and you get the charge of protons and neutrons. But quarks are strange. You can never isolate one. The strong force that binds them gets stronger the farther apart they are. Like a rubber band. Pull quarks apart and eventually you create new quark pairs from the energy. You never get a lone quark. This is called confinement. Quarks come in 6 types called flavors: up, down, charm, strange, top, bottom. Only up and down are stable. The others decay rapidly into lighter quarks. There are also leptons, electron-like particles. The electron itself, the muon, the tau, each has an associated neutrino, ghostly particles with almost no mass that barely interact with anything. Trillions pass through your body every second. You never notice. Matter is built from 12 fundamental particles, 6 quarks, 6 leptons. These interact through 4 forces: electromagnetism, the weak nuclear force, the strong nuclear force, and gravity. Each force is carried by particles. Photons carry electromagnetism. Gluons carry the strong force. W and Z bosons carry the weak force. Gravity should be carried by gravitons, but we've never detected them. This is the standard model of particle physics, developed through the 1960s and 70s, confirmed through thousands of experiments. It explains everything we've ever observed about particles and forces, except gravity. And a few other problems. The standard model says particles should be massless, but they're not. Why? In 1964, Peter Higgs and others proposed a solution: a field permeating all space. Particles interact with this field. The interaction gives them mass. The more strongly a particle interacts, the more massive it is. This is the Higgs field. If it exists, it should have an associated particle, the Higgs boson. Finding it required the largest machine ever built, the Large Hadron Collider at CERN, a ring 27 kilometers around, buried underground on the French-Swiss border. It accelerates protons to 99.9999% light speed and smashes them together 40 million times per second. In 2012, they found it, the Higgs boson, mass 125 times a proton, exists for 10 to the negative 22 seconds before decaying. But it's there, the final piece of the standard model, confirmed. So atoms are made of electrons orbiting nuclei, made of protons and neutrons, made of quarks held together by gluons with mass given by the Higgs field, interacting through forces carried by photons and W and Z bosons in a quantum framework that describes everything as probability waves collapsing when observed. This is what matter is, but we're not done, because the standard model, for all its success, is incomplete. The standard model explains everything we've observed in particle physics, except it doesn't explain dark matter, or dark energy, or why gravity is so weak, or why there are 3 generations of particles, or why neutrinos have mass, or what happened to antimatter. The universe we can see, touch, measure is 5% of everything that exists. The rest is dark, invisible, unknown. Start with dark matter. Galaxies rotate too fast. Stars at the outer edges move at speeds that should fling them into space. They don't. Something invisible is holding them in. We call it dark matter. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically, but it has mass. Lots of it, 5 times more than ordinary matter. We know it's there because we can see its gravitational effects. Galaxies bend light from objects behind them. Einstein's general relativity predicts this. But the bending is stronger than visible matter can explain. Something invisible is adding mass. Dark matter could be made of particles we haven't discovered yet. WIMPs, weakly interacting massive particles. Or axions, ultralight particles that barely touch anything. Or primordial black holes formed in the early universe. We've built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with an atomic nucleus. Nothing yet. Decades of searching. No signal. Then there's dark energy. In 1998, astronomers measured distant supernova, Type 1 supernova, exploding white dwarf stars. They're standard candles. We know their brightness. By measuring how dim they appear, we calculate their distance. The supernovae were farther away than expected. The universe isn't just expanding, It's accelerating. Something is pushing space itself apart. We call it dark energy. It makes up 68% of the universe. We have no idea what it is. Einstein's equations allow for a cosmological constant, a property of empty space itself. Space has energy even when nothing is in it. This vacuum energy could drive acceleration. But when you calculate what the vacuum energy should be, you get a number 10 to the 120 times too large. The worst prediction in physics. Either the calculation is wrong or something cancels out almost all the vacuum energy. We don't know which. Gravity is also a problem. It's extraordinarily weak compared to other forces. The electromagnetic force between two electrons is 10 to the 42 times stronger than gravity between them. Why? One possibility is extra dimensions. Space might have more than 3 dimensions. The others are curled up so small we can't detect them. Gravity could be leaking into these extra dimensions. That would explain why it seems weak in our 3-dimensional world. String theory predicts this. String theory says particles aren't points. They're tiny vibrating strings. Different vibrations produce different particles. Electrons, quarks, photons, all different notes played by the same fundamental string. It's elegant. It unifies quantum mechanics and general relativity. But it requires 10 or 11 dimensions, and it makes almost no testable predictions. We can't prove it, we can't disprove it. It sits in mathematical limbo. The Standard Model has 3 generations of particles. The electron, muon, and tau are identical except for mass. Same with their neutrinos, same with the quarks. Up and charm and top. Down and strange and bottom. Why 3? Why not 2? Why not 5? We don't know. The particles seem arbitrary. The Standard Model doesn't explain their masses or why they exist in this pattern. And where did antimatter go? Every particle has an antimatter partner. Positron for electron, antiquark for quark. When matter and antimatter meet, they annihilate. Pure energy. The Big Bang should have created equal amounts of both. They should have destroyed each other. The universe should be empty, but it's not. Matter won. By a tiny margin. For every billion antimatter particles, there were 1,000,000,001 matter particles. The excess survived, became everything. Why was there an asymmetry? The Standard Model allows for small matter-antimatter differences, not nearly enough to explain what we see. Something happened in the first moments after the Big Bang, something that favoured matter. We don't know what. Then there's the measurement problem. Quantum mechanics says particles exist in superposition until measured. Measuring collapses the wave function. But what counts as a measurement? Does it require a conscious observer? Does the universe need us to exist? Or does interaction with any large system count? We've avoided this question for a century. The math works. Shut up and calculate. But the philosophical implications remain. What is real before we look? Some physicists embrace the many worlds interpretation. Every quantum measurement splits the universe. All possibilities happen. You measure a particle's spin. In one universe, it's up. In another, it's down. Both are real, both exist. The universe branches endlessly. It solves the measurement problem. No collapse needed, but it multiplies reality beyond imagination. Infinite universes for every quantum event. Occam's razor screams. Yet the math is clean. Others prefer pilot wave theory. Particles have definite positions always, guided by a quantum wave that fills space. Measurement reveals what was always there. No collapse, no split universes, just hidden variables we can't access. Einstein liked this. God doesn't play dice, but pilot wave theory is non-local. Information travels faster than light in the guiding wave. That troubles people. Or maybe quantum mechanics is incomplete. Maybe there's a deeper theory underneath. A theory that explains why the universe appears probabilistic when it's actually deterministic. We haven't found it. Bell's theorem proved that certain types of hidden variable theories can't work. The universe really is non-local, really does have quantum correlations that Einstein called spooky action at a distance. Entangled particles influence each other instantly across any distance. We've tested this. It's true. The universe operates on principles we can describe mathematically, but not always understand intuitively. Quantum field theory works. The standard model predicts particle interactions to 15 decimal places, but it doesn't tell us why the laws are these laws, why this universe, why these constants. The fine structure constant, alpha, determines electromagnetic strength. It's approximately 1/137. Why? Nobody knows. If it was slightly different, atoms couldn't form, stars couldn't burn, life couldn't exist. The cosmological constant, the mass of the Higgs, the strength of gravity, dozens of parameters seem fine-tuned. Change any of them slightly, and the universe becomes sterile. No stars, no chemistry, no observers to wonder why. Some invoke the anthropic principle. Of course, the universe allows life. If it didn't, we wouldn't be here to notice. If there are infinite universes with different laws, we naturally find ourselves in one that permits our existence. Selection bias. But this feels like giving up. Like saying the universe is random and we're lucky. Others see design. A creator who set the constants precisely. This is religion, not science. It doesn't predict anything. Doesn't explain anything. Just pushes the question back. Why did the creator choose these values? Maybe the constants aren't constant. They could vary across space or time. Early universe might have had different physics. Or they could be determined by some deeper principle we haven't discovered. A theory of everything that predicts all the parameters from first principles. String theory attempts this. Loop quantum gravity attempts this. Other approaches exist. None have succeeded. The mathematics becomes impossibly complex. We can't solve the equations. We're also limited by our tools. The Large Hadron Collider is the most powerful particle accelerator ever built. It reaches energies that existed a trillionth of a second after the Big Bang. But to probe the Planck scale, where quantum gravity effects appear, we'd need an accelerator the size of the galaxy. We'll never build that. We're stuck observing indirect effects. Subtle anomalies, rare decays, cosmic rays, looking for hints of physics beyond the standard model. Some hints exist. Neutrinos have mass. The standard model says they shouldn't. We don't know why they do. The masses are incredibly tiny, 1,000,000 times smaller than electrons, but not zero. Something gives them mass. Probably not the Higgs mechanism. Something else. We call it the seesaw mechanism. Heavy partner particles existed in the early universe. They decayed but left behind tiny masses for neutrinos. Maybe. We haven't found the heavy partners. Muons, heavier cousins of electrons, have a magnetic moment. How much they respond to magnetic fields. The standard model predicts this. Experiments measure it. The values don't match. The discrepancy is small. 3 standard deviations. Could be experimental error. Could be new physics. We're not sure yet. More data is coming. The universe is also teaching us through astronomy. James Webb Space Telescope, launched in 2021. It sees farther than Hubble, farther than anything before. It's finding galaxies that shouldn't exist, massive galaxies in the early universe. Too big, too soon. They shouldn't have had time to form. Maybe our models of galaxy formation are wrong. Maybe dark matter behaves differently than we think. Maybe something about the early universe surprises us. Gravitational waves arrived in 2015. LIGO detected ripples in space-time from colliding black holes. We're now listening to the universe in a new way. Not light, not particles, gravity itself. Neutron stars merge. We detect the waves. We see the explosion in light. We measure gamma rays, X-rays, optical, radio, multi-messenger astronomy. Every wavelength telling part of the story. We're learning how heavy elements form, how black holes grow, how space-time bends. But we're also confronting limits. The observable universe is 93 billion light-years across. We can never see beyond that. Light from farther away hasn't had time to reach us. The universe is expanding. Eventually, distant galaxies will accelerate away faster than light. We'll lose sight of them. In trillions of years, only our local galaxy cluster remains visible. Everything else disappears beyond the horizon. Future astronomers won't see the cosmic microwave background, won't know the Big Bang happened, won't be able to reconstruct cosmology. The evidence will be gone. We exist in a brief window. The universe is 13.8 billion years old. Stars will shine for trillions more. But the era where we can observe the universe's history, where we can see the afterglow of creation, is temporary. We're lucky to be here now, to see the cosmic microwave background, to measure the expansion rate, to detect gravitational waves from the early universe. This moment won't last, so we're building telescopes, detectors, accelerators. We're asking questions. Why is there something rather than nothing? Why these laws? Why this universe? We may never answer completely, but we can push further, understand deeper, reveal more. The story of atoms is the story of curiosity. From Democritus imagining indivisible particles to Rutherford discovering the nucleus to Heisenberg, formalizing uncertainty to Higgs predicting the mass field. Every step was someone asking why, someone refusing to accept the surface explanation, someone demanding to know what lies beneath. That drive continues. Experiments run day and night. Particle colliders smash protons. Neutrino detectors wait underground. Gravitational wave observatories listen for space-time ripples. Dark matter searches filter billions of events looking for one signal. The work is slow, painstaking. Most experiments find nothing, but occasionally something appears. An unexpected result, an anomaly, a hint that our picture is incomplete. And then the real work begins. Testing, verifying, explaining. Building new theories, making predictions, designing new experiments. The cycle continues. You're made of atoms that are mostly empty space. Your body is quantum fields fluctuating. The particles that compose you existed in stars that exploded before the sun formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all forged in stellar cores. You're made of star stuff, as Carl Sagan said. But more than that, you're made of quantum uncertainty, of probability waves, of fields permeating space, of quarks confined by forces we barely understand, of mass granted by a field we only discovered 12 years ago. You're made of questions, of mysteries, of physics we're still unraveling, and every time you wonder about the world, every time you ask why, you're continuing the same journey that began 2,500 years ago with a Greek philosopher staring at the sea. The atoms that compose you are the atoms that compose everything. You're not separate from the universe. You're part of it, made of it, experiencing itself. The universe looking back at itself through your eyes. That's what you are. That's what atoms are. The foundation of reality, the building blocks of existence, the question that never stops asking itself. What are we made of? We return now to where we began, to Democritus, the laughing philosopher, watching his city condemn him for wasting his inheritance on knowledge. He saw atoms, he saw void, he saw the truth so clearly that it took humanity 2 millennia to catch up. He was wrong about many things. His atoms weren't indivisible. They have structure, complexity, internal worlds of quarks and gluons and quantum fields. His mechanistic universe couldn't account for consciousness, for choice, for the strange probabilistic dance that governs the quantum realm. His certainty that atoms explained everything ran into problems he couldn't solve with the mathematics available to him. But he was right about the essential thing. The universe is made of fundamental units. Reality has a bottom. There's structure beneath the surface, patterns beneath the chaos, laws that govern how everything works. That insight, that simple, radical claim that matter is made of tiny invisible particles moving through empty space, became the foundation of science itself. Not because Democritus proved it, he couldn't, but because he dared to think it. Because he refused to accept that the world was too complex, too mysterious, too divine to be understood through reason alone. The path from Democritus to the standard model is not a straight line. His ideas were forgotten, dismissed, buried under centuries of Aristotelian orthodoxy. They resurfaced in fragments, half-remembered, transformed. Epicurus took his atoms and built an ethics. Lucretius turned them into poetry. Dalton made them scientific. Rutherford split them open. Each generation added layers. Electrons, nuclei, protons, neutrons, quarks, gluons, the Higgs field. Each discovery revealed that what seemed fundamental was actually composite. What seemed simple was actually complex. The bottom kept receding, and yet we're closer now than Democritus could have imagined. We've measured the fundamental particles, we've calculated their masses, we've tested the theories to 15 decimal places, we've built machines that recreate conditions from the first moments after the Big Bang. We've looked deeper into matter than any ancient philosopher dreamed possible. The questions that remain are not whether atoms exist. They do. We've seen them, photographed them, manipulated them one at a time. The questions are what lies beneath, whether quarks are truly fundamental or made of something smaller, whether space-time itself is quantized, whether the universe has extra dimensions we can't perceive, whether the constants that govern physics are truly constant or vary across space and time. These are Democritus's questions, asked with better tools. The same curiosity that made him laugh at the absurdity of existence drives physicists to spend careers staring at detector readouts, waiting for a signal. The same refusal to accept easy answers that made him unpopular in Abdera makes modern scientists question theories that have worked for decades. The atoms you're made of are 13.8 billion years old. They've been through multiple stars. They've been scattered across space, pulled together by gravity, fused in stellar cores, blown apart in supernova. They've been parts of other things, other planets, other creatures, other configurations. Before they were you, they were something else. After you, they'll be something else again. You're a temporary arrangement, a pattern that matter has fallen into for a brief cosmic moment. The atoms will persist, the pattern won't. This isn't depressing, it's liberating. Democritus understood this. The atoms don't care about your anxieties, your fears, your desperate need for permanence. They just exist, they move, they combine and separate according to laws that have no interest in your personal drama. And yet here you are, conscious, thinking, wondering, made of atoms that somehow organize themselves into a structure complex enough to contemplate its own existence. The universe has become aware of itself through you. The same quantum fields that make up quarks and electrons have arranged themselves into neurons and synapses that generate thoughts about quantum fields and quarks and electrons. That's the real mystery, not what atoms are made of. We're figuring that out. The mystery is how atoms made us, how unconscious particles following simple rules created consciousness, how physics became chemistry, became biology, became thoughts, feelings, the experience of being someone rather than something. We don't have the answer yet. Maybe it's emergence, complex systems developing properties that their components don't have individually. Maybe it's quantum effects in microtubules. Maybe consciousness is fundamental, a property of matter we haven't measured yet. Or maybe we're asking the question wrong. Maybe consciousness isn't a thing that needs explaining, but a process, an activity, a pattern of information flow that happens when certain systems reach sufficient complexity. The atoms don't tell us, they just continue their quantum dance, existing in superposition, collapsing when measured, entangling across distance, behaving like particles and waves simultaneously, following the Schrödinger equation, obeying conservation laws, building everything from quarks and gluons according to rules we've mapped but don't fully understand. Democritus laughed because he saw through the illusion, saw that everything people take seriously, wealth and power and status and legacy, is just atoms temporarily arranged. Nothing lasts, nothing matters in the cosmic sense. The atoms will outlive your concerns by billions of years. But he missed something. The temporary arrangements matter to those experiencing them. You're not just atoms, you're atoms that care about being atoms, that wonder about their origin, that build particle colliders to smash themselves together, just to see what happens, that write equations describing their own behaviour, that create art and music and stories about what it means to be a conscious pattern in an unconscious universe. The atoms that compose you have been doing this for nearly 14 billion years, combining, separating, forming stars and planets and creatures. This particular combination, this specific pattern that is you, has never existed before and will never exist again. You're unique in the history of the universe. When you die, when your atoms disperse and recombine into other things, this pattern is gone forever. That's not nihilism, that's urgency. You have this brief window of existence, this moment of consciousness, this chance to observe the universe, to understand it, to add something to the great project of figuring out what reality is and how it works. Democritus spent his inheritance travelling the ancient world, learning everything he could, thinking thoughts that wouldn't be proven for 2,000 years. He returned home to prosecution, to mockery, to a city that thought he'd wasted his life on useless abstractions. But he kept thinking, kept laughing, kept trying to understand. The atoms that made him are still here, scattered now, part of soil, air, water, other living things. The pattern that was Democritus dissolved long ago, but the thoughts remain, the questions persist. The curiosity that drove him to imagine atoms echoes through every laboratory where someone is trying to understand matter at its deepest level. This is what we pass forward. Not our atoms, those get recycled, not even our specific insights. Democritus was wrong about atoms being indivisible. We'll be wrong about things too. Future physicists will look back at the standard model, the way we look back at classical atoms. Useful, correct in its domain, but incomplete. What we pass forward is the commitment to asking, to not accepting the surface answer, to demanding that the universe explain itself, to building the tools, running the experiments, doing the mathematics, following the evidence wherever it leads, even when it leads somewhere uncomfortable. The universe doesn't owe us comprehensibility. It could have been random, chaotic, impossible to understand. Instead, it follows rules, mathematical rules, rules we can discover through observation and reason. That's the miracle. Not that we exist, but that we can understand. Every equation we derive, every particle we discover, every measurement we make adds a piece to the picture. The picture is incomplete. It will always be incomplete. There's always another layer, another question, another mystery beneath what we thought was the bottom. But that's not failure, that's the point. The universe is a puzzle that keeps generating new puzzles as you solve it. Reality goes deeper than we can imagine. And that's wonderful. That's what makes the project worth continuing. The atoms you're made of don't know they're part of you. They don't know they're part of anything. They just exist following quantum mechanical laws, fluctuating in fields, maintaining their quark structure through the strong force. Unconscious, unaware, pure physics. And yet here you are, reading these words, understanding them, thinking about atoms, thinking about themselves. The universe performing the most elaborate magic trick imaginable, making consciousness appear from pure mathematics and quantum fields. Democritus would have laughed at that too, not from cynicism, from joy, from the sheer absurdity and wonder of a universe that can do this, that can take quarks and electrons in the Higgs field and arrange them into something that asks what quarks and electrons and the Higgs field are. The atoms continue, the questions continue, the search continues, and somewhere in there, briefly, impossibly, you exist, made of stardust and quantum uncertainty and 14 billion years of cosmic evolution, asking what you're made of, finding answers that only lead to better questions. That's what atoms are. That's what you are. That's what this whole strange, magnificent universe is. Questions asking themselves. Reality trying to understand reality. Consciousness emerging from unconsciousness just long enough to look back at the void and laugh.